We are going to take the limit of these sequences. We want to find the limit of these sequences, and I want to point out one thing. The form of these sequences, if we look carefully at them, as we think about n going to infinity, the form is going to be 1 to the infinity for both of these. So for this top one, as n goes to infinity, 3 over n goes to 0. So this base here goes to 1 and the exponent goes to infinity. This is an indeterminate form. And the technique that we're going to use, this log limit process, is for sequences of this indeterminate form. Similarly, down below, when we take the limit in here, the quotient here will have a limit of 1 because these are polynomials of equal order with coefficient 1 over 1. So that limit is 1. Or you could apply L'Hopital's rule here and take the derivative of the numerator, get 1, take the derivative of the denominator, get 1, 1 over 1 is 1, and then 1 to the infinity. So both of these are indeterminate, and that's why we need this special process here to deal with these indeterminate limits. To find the limit of these, we are going to end up using a derivative process, and in order to get to that place where we take derivatives, we are first going to rewrite these sequences as functions of x, just because typically we think of a function of x as a continuous, as having a continuous domain, x being a real number, whereas n we usually think of as coming from the integers or the positive integers or something. So I've rewritten the sequence as a function of x. I'm going to take the natural log of both sides so that we can bring down the exponent on the right. When we take the natural log of both sides, we can then apply the log property that says that coefficients can become exponents and vice versa. We are now going to take the limit of both sides of this equation, and when we take the limit on the left-hand side, the limit can move inside the log function. We're taking the limit as x goes to infinity. And on the right-hand side, we take the limit as x goes to infinity. And I'm going to rewrite the right-hand side so that it will be in a form that allows us to apply L'Hopital's rule. So I'm going to move that 2x into the denominator as a fraction. So dividing by 1 over 2x is the same thing as multiplying by 2x. And when we do this, what we see is that as x goes to infinity, the numerator is going to go to 0, and the denominator is going to go to 0. So I'll indicate that by just putting zeros here over the equal sign. Not standard notation, but it's just a cue that, oh yeah, we can now apply L'Hopital's rule. And L'Hopital's rule says take the derivative of the numerator and divide it by the derivative of the denominator. In other words, the limit of a quotient is the same as the limit of the quotient of derivatives. So to take the derivative of the numerator, when we differentiate a log, the first thing we do is take 1 divided by the argument of the log. So 1 over what's inside the log. And then we have to multiply by the derivative of what's inside the log. The derivative of 1 is 0. The derivative of 3 divided by x, if we need to, we can come off to the side and write that as 3x to the negative 1, and then take the derivative of that using the power rule. So the negative 1 comes down, creating a negative 3, and then we subtract 1 from the exponent. And if we wrote this without negative exponents, we would write it as negative 3 divided by x squared. So let's go ahead and do that. So negative 3 divided by x squared. And in the denominator, we'll do something similar. We can rewrite that 1 divided by 2x as 2x to the negative 1. That's a little easier to differentiate. Remember that that negative 1 power is on the entire quantity 2x. It's not just on the x. The 2 is also in the denominator. And so when we rewrite it like that, and then take the derivative. We bring down the negative. We subtract 1 from the exponent. But then we also have a chain rule, and we have to multiply by the derivative of the inside, which is a 2. And so this will give us, if we rewrite this without negative exponents, in the denominator we'll have 2x quantity squared, which would be 4x squared. One of the 2's will cancel, giving negative 1 over 2x squared. So that is what is going to be in our denominator now. So the next step is going to be to clear out some of these fractions. Before we clear out the fractions, though, let me just point out one other thing about taking the derivative of that denominator. Another option is to write it as 1/2 x to the negative 1. So we can simply pull up just the x to the numerator and not the 2 also. And if we do that, if we use that method, then when we differentiate, the 1/2 is a constant that floats through. We differentiate x to the negative 1, the negative comes down, we subtract 1 from the exponent, and then to eliminate negative exponents, we move the x to the negative 2 into the denominator by making its exponent positive. So 2 different ways that you could differentiate that term in the denominator, whatever makes the most sense to you. So now let's clean up this fraction over here. So we've got a lot going on. And what we're going to do is bring this denominator up to the numerator by reciprocating it. So I'm going to write everything as fractions up here. So we still have this. We still have this. And then the only step I'm going to make here is flip that fraction in the denominator so that we have that. This allows us to see some cancellation. The x squareds are going to cancel here. And we can then write this as the limit of, let's see, combining constants is going to give us 6. And then in the denominator, we have this. And I'm going to go ahead and put the subscript on the limit back in because now we're going to apply it. And we have a limit that we can calculate now. This term here, 3 over x, as x goes to infinity, will go to 0. So this whole limit will become 6. And that leaves us with a left-hand side that's not quite simplified yet. We still have a log over there. And our goal is to isolate this limit quantity. That's what our overarching goal is. We want to find the limit of this function y. And right now we have the log of the limit of y. And so all we need to do is exponentiate both sides. And then on the left, we'll have limit of y as x goes to infinity. And on the right-hand side, we'll have e to the 6. So that will be our limit. Okay, so now let's do the second one. I've taken the second one, which is presented as a sequence where n is a positive integer greater than 3 ostensibly. We wouldn't want division by 0. I've switched it over to a function of x, indicating that x is now a real number. That allows us to take derivatives. We can't take the derivative of a discrete function like a sequence, so we're thinking of our sequence embedded into this continuous function. Once again, we're going to take the log of both sides with the sole purpose of bringing that exponent down. There's our log property. We now take the limit of both sides, and once again on the left-hand side, the limit as x goes to infinity can move inside the log function because the log function is a continuous function. And on the right-hand side, we take the limit as x goes to infinity. And we know that our goal is to use L'Hopital's rule. And so what we're going to do is rewrite the right-hand side as a fraction. And this time I'm going to do it a little bit differently than I did the other one, just to mix it up a bit. So in the last one, I brought down the entire coefficient quantity here This time I'm only going to bring down the x. I'm going to think about the 4 as a constant in the numerator. And then in the denominator, I'm just going to bring down that 1 over x. So this is fine. We can do that. Dividing by 1 over x is the same as multiplying by x. That coefficient of 4 will just factor to the front once we take the limit. Now we're noticing an important feature here, and that is that the denominator goes to 0 and the numerator goes to 0 as x goes to infinity. Let me make sure that you're clear on that. When we let x go to infinity here, inside that log we have infinity over infinity, an indeterminate form. And you can evaluate that limit as x goes to infinity in a couple of ways. You could apply L'Hopital's rule. The derivative of the numerator is 1, the derivative of the denominator is 1. And then the log of 1 is 0. You could also, excuse me, you could also remember that when you have a quotient of polynomials that have matching powers, matching degrees, if these leading terms have the same degree, the value of the limit is the ratio of leading coefficients. So whichever way works, that's fine. Now we're applying L'Hopital's rule, which is why I put the 0 over 0 next to the equal sign just as a q. And if we look at the numerator, the derivative of a constant times a function is that constant times the derivative of the function. So the derivative of this log, we first reciprocate the argument. We reciprocate what's inside the log. And then we have to take the derivative of what's inside the log. Well, what's inside the log is a quotient, so we have to use the quotient rule. So we're going to do low times the derivative of high, so low d high minus high d low, the derivative of the denominator, all divided by the denominator squared, low squared. So low d high minus high d low over low squared. And then the derivative down below, we can think of that as x to the negative 1. When we differentiate that, we use our power rule for derivatives. And if we write it without a negative exponent, we would have that. So that will be in our denominator. Now let's do a little bit of rewriting here. So in the numerator, we have 4 multiplied by x minus 3 divided by x. Let's clean up this numerator a little bit here. So this is going to be x minus 3 times 1, that's just x minus 3. X times 1 is just x. So we have x minus 3 minus x. So the x's are canceling out, and we're left with minus 3. And then x minus 3 quantity squared. And now we're flipping this fraction that we're dividing by, and we're going to do some simplification now. So we'll have limit. We still have the 4. Now, one of these x minus 3's is going to cancel. So we'll be left with 1 x minus 3 in the denominator. And one of these x's will cancel, leaving us with 1 x in the numerator. And so what we can write next then is 3. The minus 3 and the minus 1, these will also turn into a positive. So in the numerator, we're going to have 3x. And in the denominator, we are going to have x minus 3. When we do all of our simplification there. And when we apply the limit, and let's get that subscript back in here now that we're going to actually apply it. So the constant floats, and then we are looking at this fraction, which you can again think of in two ways. You could say, hey, we're getting the indeterminate form infinity over infinity. So we take the derivative of the numerator and get a 3, take the derivative of the denominator and get a 1. 3 divided by 1 is 3. Or you could say, these are polynomials of equal degree, so the limit at infinity is going to be the ratio of leading coefficients, which is also 3. So we end up with a limit of 12. Now that limit is not for the limit of just y. We have a natural log on the other side, so we want to exponentiate both sides so that our limit will be e to the 12. And that is how we use the log limit process to evaluate limits of sequences.